Hey guys, thanks for tuning in once again. Let's see, what's the topic of this video? Oh yeah, these are some of the trickiest problems, or they can become some of the trickiest problems in all of equilibrium, I think. Acids and bases, perhaps buffers as well. But I just wanted to work out a few more of these weak acid problems. You hopefully have seen a few already. But anyway, so the general form, for the general representation of a weak acid, we just call it HA. The H is the hydrogen ion, the A is the counter ion, the negative part that could be very complicated or very simple, but we want to just keep it simple. A is for acid. Sometimes we'll specify what that formula is, but as long as you see the hydrogen in front, you're hinted in a way that they could be acidic or basic, anything negative or something with negativity to it. So this B probably has some lone pairs on it. The negative lone pairs, negativity of the lone pairs are attracted to that proton, the hydrogen ion. And if I write these two on the top and that on the bottom, or these two on the top and that on the bottom, ignore the pure liquid water, I get the common expressions for Ka and Kb for any general acid. Here's one. I'm just making this up. I think I'm making this up. I don't think I looked up, but I'm pretty sure there are so many hundreds, maybe even thousands of weak acids. I'm sure I could find a hydrogen that would come off to the tune of, dissociate, I should say, to the tune of 2.7 times 10 to the minus 10. And that means that a little bit of this dissociates and a whole lot of the acid stays intact. But in any case, I'm imagining a 0.22 molar solution of this weak acid. My question probably is, if they give me a Ka, what is the pH of this acid? This is a description of how much this weak acid breaks apart. The concentration, 0.22 molar, does make a difference in the end in terms of how much or what percent of that acid breaks apart. Well, here's the story, and by now this might look a little bit familiar. But I say something like HA in the water. I have no hydrogen ion and no counter ion in the beginning. So I call those zeros, and I put the molarity over here. That's initially. The change, well, if I have none of this and none of this, they both go up a little bit, and this goes down a little bit. Usually our simplest case, which is why we like to keep it simple, one of these creates one of these and one of these, so these x's are all the same, which is not always true in general equilibrium. This goes from 0 plus x, 0 plus x. This is 0.22 minus x. But if you tried a few of these problems already, you know what we like to do. We like to assume x is small, because in the numerator I'll have these two x's, but in the denominator I'll have this. But that would lead to a quadratic if I didn't assume that this x is small compared to 0.22. And indeed, sometimes you can't do that. Maybe I'll get to a question like that in a little bit. But in any case, I write the equation for Ka like I'd done before. I knew I was given the Ka in this question, and I set this in the top, this in the top, that in the bottom. Again, that's really 0.22 minus x, but I'm assuming x is so small that I can ignore it for the sake of simplicity and solving this little algebraic expression. This particular x came out to 0.00000007 or something like that. I missed a zero. That's too many zeros. Small number, small molarity. This is very, very close to neutral water anyway. That constant 10 to the negative 10, that's a weak acid. And so 1 times 10 to the negative 7, a little bit smaller, would be the hydrogen ion concentration in pure water. Take the negative log, and you're done. It's never a bad idea to go back and check your assumption. Did this x come out to be small compared to 0.22? In other words, what's 0.22 minus 0.00000771? The answer to 2 sig figs, it is still 0.22. So I'm pretty safe in that assumption. Talk more about that in a minute, perhaps. And of course, a pH of 5 is lower than 7, so that's an acid. To some degree, we expected that anyway because we are doing a weak acid problem. We might also calculate what we call the percent dissociation. Oh yeah. So this is my hydrogen ion concentration. This is my original acid, HA, and basically the acid in solution as well. Divide the two, comes out to an incredibly small number, an incredibly small dissociation, percent of dissociation. If I did my math right, I just did this mentally, but something like if I had 10 billion HA weak acid molecules in the water, only 35, that's what that 35 stands for, only about 35 of them would dissociate. I'm sure somebody will come tell me that's wrong. It's something close to that, though. 10 billion. Some outrageous number. Outrageously large number. Say, like my new background. Purple with polka dots. Here's another one. The variation on the problem is, I have a beginning concentration of my acid, but I take a pH probe and I just measure the pH of that solution. So you put 0.095 moles per liter of HA in water and measure the pH. It comes out to 4.11. As soon as they tell me the 4.11, I think to myself, I'm going to need to take that and get a hydrogen ion concentration. So I take 10 to the negative pH, 10 to the negative 4.11 to find my molar concentration of hydrogen ion. Then from that I can take and make an ice table if I'd like, but honestly I really don't have to. I could just think about, if I know this H plus, then I know the A minus, because they're both always, as far as these problems go, they're always the same. This 0.095 decreases a little bit by 0.0000776, but if I subtract this from this, maybe I should subtract. Yeah, that'd be a more thorough answer, a more complete answer. Let's see what I did down here. I went ahead and set up a table. Or you can try it. 0.095 minus 0.0000776 comes out to 0.0949 something or other. And if you round it to 2 sig figs, it's still 0.095 anyways. And I got the Ka value, 6.1 to negative 6. So that's the other variation, where they tell you the pH. So they tell you these numbers. In essence, they're disguised as a pH, but you just twist it around algebraically with the anti-log, or the 10 to the power x, and 10 to the negative pH gives you the H plus amount, and also this amount, and these two amounts in the numerator are the same. You crank out a Ka value. Pretty simple. We might check this dissociation and see if that was a good assumption, that this really is small. 0.0000776 divided by 0.095, the beginning concentration, was 0.0817%, which is very small. Here's a rule of thumb, and it usually works. It's generally accepted. If your percent dissociation of your weak acid is less than 5%, then the extra small assumption is a good assumption to make. So we always check that. Always, not always. I'm lazy sometimes. I don't, but I should. Another weak acid problem. This one's tricky. This is not nitric acid, nitrous acid, 0.01 molar. Look at the constant. It's actually small but large for a weak acid. So here's the deal. If the initial concentration is small, and so this is kind of watered down, and this is a large constant, then I'm not going to be able to assume X is small. It's a bad assumption. That is to say, this strong weak acid, it's a weak acid, but it comes apart pretty well for a weak acid, dissociates so well that this X will not be small compared to this diluted 0.01, that small number there. So if that's true, and occasionally you can't make that assumption, I've seen that question on a couple of tests, but it doesn't happen very often. We like to assume X is small. But if I didn't assume X is small, X times X is X squared in the numerator. This 0.01 minus X goes over to the other side. And I solve with the quadratic formula, although I did not bother to write out my answer here. Honestly, I used an app for that. Seriously, I did. I just plugged down the A term is 1, the B term is 0.00045, the C term is negative 0.0000045. I got a negative answer. That can't be the right answer, so I chose the 0.0019, called that the hydrogen ion concentration, also the nitrite ion concentration, and take that answer for X away from 0.01, and you find it decreases it fairly substantially. In other words, if I did my the percent dissociation 0.0019, which I got from solving the quadratic formula, compared to the original concentration of 0.01, that's 19%. And the rule of thumb was anything less than 5% was a good assumption that X is small. Did I not? I did not. I should go ahead and take the negative log of that. So what's the negative log of 0.0019? That gives you the pH. No, wait, duh. They told me the pH. No, they didn't. Yeah, the question is, what's the pH? They give me the constant. Right, they give me the constant, and I'm supposed to find the pH. So whatever the negative log, I didn't write that down. Maybe I should before I post this PDF. Negative log of that gives me my pH. But anyways, good example of how you can't always assume X is small, but with weak acids and weak bases, you almost always can assume that. All right, let's do a weak base problem. They're very super similar. The only difference is, which seems to confuse some students, is the water is thrown in there as one of the reactants. So this weak base in water actually pulls the water apart a little bit. There's like a lone pair here, pulls the H plus off of the water. The Kb for this, in this case, given to me. So I suppose I'm supposed to find the pH. First of all, of course, I'll find the OH minus amount. So I start off with 0.18 molar. They must tell me that number. Oops. There we go. And none of the H plus and none of the HB plus and none of the OH minus. But then as I proceed in the equilibrium in the water is established pretty quickly. I have this goes up and this goes up and this goes down. But the classic assumption is, again, if the Ka is small and this is not too watered down, good assumption that X is small. Saves us a lot of time. I look back to my definition of the equilibrium constant expression, and I write that quickly in a heartbeat. And my X's are the unknowns. I don't know those up there. 0.18 minus X is very close to 0.18. Solve for the X. Oh, let's see. I better shrink down just a little bit here. Solve for X, and that X, remind yourself what X is. Got to go back up to the table and say, what is X? Oh yeah, X is the OH minus amount. So from that I can easily find a POH, and then from that I can easily find a pH. And it's always good to check your assumption too. 0.00011 divided by the original concentration, only 0.061% dissociation, probably because that constant for the Kb is so small. Oh yeah, by the way, we don't call this, sometimes we call this percent hydrolysis because we're actually interacting with the water, breaking water apart. So of that 0.18 molar weak base, only 0.061% of that dissociated the water. If I have time for one more problem, I might. Here's Adeline, a weak base. It all looks complicated except we just focus on that lone pair right there on the nitrogen. Nitrogen is famous for having a lone pair that can function as a weak base dissociating the water. All this other junk, I could just replace that with a hydrogen and I'd get ammonia back, which I know is a weak base as well. The Kb for this, so in simple terms, I have B, HOH, equilibrium. In this one I'm going to, oh, what the, curious. Let me just roll with it. I have 2 minutes left. I have a pH written down here. I hope, usually they tell you the pH or the Kb, or they tell you the Kb and want to know the pH. I think I'm going to end up driving the Kb again. Oh well. Thanks for being patient with me. So the pH was given to me. I get the POH because I'm dealing with bases, and that's 5.35. 10 to the negative POH gives me the OH minus concentration. Then I can take that 4.47 to negative 6, small number, plug it back in my table, and I solve for Kb, which I should erase it from my PDF from above. Was it 4 times 10 to negative 10? I hope it was. Oh, yeah, close, 3.9. So it must have had a little rounding boo-boo somewhere. Anyways, doesn't this look just like a weak acid problem? And if I was not lazy, I should check my percent. I could call it ionization or hydrolysis. This is my small amount. My goodness, that's so small. So in a way, the percent hydrolysis is just like the Kb calculation for different reasons, but I don't square the top one there. You see that? This is the same as this. You just don't square that one there. Yeah. Guys, I'm out of time. Thanks for watching, and I'll catch you in class. Thanks for working hard.